All right, so so for today we're gonna first of all finish the lecture slides I prepared for last time. We don't have much left to do. Some kind of summarizing and then some kind of brainstorming exercises for you all to refresh what we have learned in Plan 347 Bayesian statistics, and then just think about those materials before and then how those can be helpful for what we're going to do now. And so last time we were here, what do you mean by synthetic data approach for confidentiality protection? In particular, we are trying to estimate Bayesian statistical models on the confidential original data set. You learn as much as you can from those models, and then you simulate records based on the estimated models that you have. Okay, and then when we say simulate, we talked about last time, it's really doing posterior prediction. Okay, posterior predictive, because you're essentially trying to generate new data out of the model. And then in the past, we did that, and today we're going to go through the details using the example that how we can do it. But at the end of the day, we are trying to do posterior predictive distribution generation, and then you'll be able to get fake data out of them, but it's supposed to be helpful, that will preserve important relationships of the variables they want to keep. At the same time, will reduce the disclosure risks. Okay, so we talked about different types and disclosure risks last time. And lastly, let's make sure that we know when you're releasing synthetic data, we're talking about, let's say, if you have a data frame and you have one variable that you want to protect. So we're saying that everything else doesn't change, but you change or you synthesize for this particular column, if you think about a data frame case. Then at the end of the day, you're returning a data frame that is synthetic, but has the same dimension, right? In a sense that whatever analysis people would like to do in the end, they are just treating the synthetic data set as if they're the original. They can do the same analysis as what they would want to do. But of course, we want to make sure that those analysis or inference will be valid. So we'll cover later in the semester how to make sure that you can get valid inferences if you have synthetic data instead of the original. Okay, but that's what we mean by the last bullet point here, that you'll be able, users will be able to do analysis for a wide class of them, especially if they have the same dimension of the database. And then whatever they want to do in the past, they could do it on the synthetic data as well. Okay, so that's an important takeaway. And so this was what I was showing you last time before we ended. I was showing you some work. Actually, like if you look at an academic journal paper about doing synthetic data, you will see that regardless of what kind of models people do, at the end of the day, they want to evaluate how good those models are for their purpose. And there are two aspects of evaluation. The first one is utility, in a sense that you want to see that any kind of estimates that you can get on the original data and on the synthetic ones, you will be able to get very close results. Okay, so one thing you could do is, say, for example, this is the example that we have trying to synthesize only the family income. And we're trying to look at, say, the mean, the median, as well as the 90th quantile. 90th quantile, all of this, the estimates and the 95% credible interval will be close to each other, like when you're comparing the data against the synthesizer. Okay, so that's one thing you can do, and that's what these tables are. And the last one is a regression analysis of a particular regression coefficient. And you can also return those estimates and then trying to compare the results on the original data against the synthetic data and see how close they are as a way to evaluate the utility. Okay, so those will be very application specific. For your project, if you do something particular, I guess, say what Reese the other day was saying, if I'm trying to work with like say synthetic data for locations or geocodes, then you might come up with other utility measures that makes most sense for what you do. Okay, so many utility measures will be very application focused or application specific, but there are some generic ones that we're going to cover later in the semester as well. So you can pick what you want to do, and of course you will have to like like focus on the applications that you want to do with the particular data set or multiple data sets that you want to work with, and use the one that makes the most sense. And that's how usually we do this type of research anyway. Like it really depends on what kind of data you want to protect. And then from there, you have to think about utility and also the risks, right? Like last time we talked about, if you have all categorical variables, it really depends on like what you assume the intruder would know. And then from there, you can come up with various measures of disclosure risks. We talked about attribute disclosure, right? And identification disclosure. But then, well, for different type of data, those measures might be computed differently. So that will be something that you have to think carefully for what you want to do. And this is an example that is from a recent research that we're trying to say that when you do synthetic data, that's this one that we should focus here. Yeah, so this are plotting identification risks, okay? Disclosure risks. And in this project, we define identification disclosure risk to be a probability. So that's why you see it's from 0 to 1, okay? And we define it to be that if it's closer to 1, it's higher chance to be identified, so it's higher risks. If it's closer to 0, it's lower chance to be identified, so it's lower risk. So this kind of violin plots that we're showing over here is really looking at the identification disclosure risk for each observation, and I plotted them side by side, okay? So this is the original data. If I just release my data in the way, people never do it, but if you do that, then this will be the risks profile for the entire data set. We have, I think in this case, a little bit more than 6,000 observations here, so that's why you see a distribution of the identification disclosures. And this is the synthesizer, the Bayesian synthesis model that we proposed, how that can help you shrink the risks. Okay? And this is another method. We don't have to get into detail now, but this is another method that can further reduce the risk. So we're trying to use this kind of visualization to show that, well, how our methods are working. And the last one is the top coding. If you remember what we were talking about last time, that especially for the consumer expenditure survey for this particular paper that we're doing, it is about 6,000-ish observations. Only about 6% of them are being top coded, okay? Meaning that the remaining 94% family income were just being released as they are, because by the time that the consumer expenditure survey program are evaluating the risks, they think those should be fine. They're not worried about them. So their policy was, well, we top coded 6% of them, with the remaining 94 being untouched. And you can see that, well, if you don't touch any of those, they never change, meaning that if you evaluate the risk, they could be really high, okay? But last time I think was really in a rush. If you focus the box at the bottom here, so if you look at the data one, the data and the top coding, so you will see that, well, the data, so data is the original data. So that seems to be smaller than the top coding, right? Meaning that, well, the top coding, it is doing something that it's supposed to be doing because it is providing protection for those records which are top coded, okay? So that's why you see a bigger size of those data observation, the count of them over here, comparing to the one in the data, okay? But the top coding, unfortunately, left the 94 untouched, and then that will still give you really high identification risk. So again, the identification risk goes from 0 to 1, and the higher the worse, the lower the better. Okay? So that will be a way. So these are different ways. I mean, sometimes people look at disclosure risks not at the record level, but at the file level. Like I return a summary statistics instead of plotting them like this. So we're going to cover different ways to do that, and then you can make your decision of what kind of visualization, what kind of comparisons you want to do. But keep in mind that you can think about disclosure risks in this case, identification disclosure risks for each record, one by one, or for the entire file. It just depends on how you want to summarize them. All right, so that's where we were last time. And today, yeah, so we talked about this, I think, last time a little bit at the beginning, but now let's put our knowledge and background into, like, from the Bayesian stats course that we took. and then to what we're doing right now. So like we said, to generate synthetic data, you first have to develop some suitable Bayesian models for your data. It depends on the data that you have, and especially depends on what kind of variables they want to synthesize. And you will have to develop different Bayesian models. Okay, so those will depend on, like we're going to talk about them today as well, but definitely depends on the goals of synthesis that you were trying to do. And then once you have your model estimated, you can generate synthetic data from the estimated synthesizer from the posterior predictive distribution. So let's just look at a toy example here. A Bayesian synthesizer, say if you have just a univariate continuous data, like family income, for example. I just have like a sequence of them. And I want to synthesize, I want to use a Bayesian method to synthesize this so we have less risk associated with each record. What you can do is, well, if I assume the family income follows a normal distribution with mean mu and variance or standard deviation sigma, and if I say, suppose sigma is fixed, let's just for simplicity, if I only trying to estimate mu, then I will put a prior for it, right? So theta is any hyperparameters for mu. I'm not using any other notations here, just theta, but you can think of, well, you know that the prior, conjugate prior is another normal, right? Like that will involve the mean and the standard deviation for the prior normal for mu. Anyway, so here we're using theta generically. So for a Bayesian synthesizer, just like what you do for a Bayesian model as well, you have the sampling model and then you have the prior for the parameters that you're working with. Okay. And then you do your MCMC and iterations. You can use JAGs, you can write your own. We can decide what you want to do, depends on the model they're working with. And then in the end, you generate those parameter draws. In our case, you generate draws for mu. And then you were trying to simulate synthetic data. So there are two general steps here. You know that if you have the parameter posterior draws of mu, you can just have them over here. Okay, so I'm using mu star here to represent the simulated posterior draws of mu to differentiate from mu itself. Okay? And then once you have that, to generate new data, synthetic data for the y's, we're using yi star here. And it's just going to come from the sampling model, okay? The sampling model is the same as what you have as you developed before. Okay? So that flow, I hope, sounds familiar to you. And we did a lot of this in 347. In short, a Bayesian model or Bayesian synthesizer, you will have to have a sampling model and then give prior for the parameters. And then you estimate your model. You generate posterior draws from your MCMC. A lot of times, if you use JAGs, it's already simulated for you. You just have to extract them, okay? And then one last step or additional step typically for the synthetic data world is that you have to simulate posterior predictive draws of new data, their prediction. So every time you're doing prediction. And the prediction, the predictive values will be the ones that we're going to use for like as the synthetic data, and then we are using them to do all of the analysis. Yes.
Is that a common practice that researchers when developing the prior model they take into account of the data?
Good point. Yeah. So Maggie's question is how we typically come up with priors, right? I mean, in short, and then. That is actually something I think in 347 we didn't explore that much. I mean, I covered certain types, for example, like a lot of times we don't know much about anything, we give a weakly informative prior, okay? So, so that will be usually, I think, the default that we will do. If you don't know anything, you probably just give something very weakly informative. And you can also, I mean, if you have strong prior information from previous studies or from a similar sample, then you can use them. So if you remember in the Bayesian linear regression section from 347, I think we talked about different ways to give priors. So we started with the weakly informative. If you don't remember, it's fine, but just give you an overview. You can do weakly informative. That typically means that, well, for this mu, is the mean. So typically you give it a normal, so it will be conjugate, right? And then you can, oh, sorry, no, in the regression context, let me just take that back. But in the regression context, remember we have, if it's simple linear regression, we have this two, sorry, beta 1, beta 0 and beta 1. They're the regression coefficients for simple linear regression. So for them, we give weakly informative prior like center at 0, because we don't know if it's going to be positive or negative, right? But then we give it a super large spread, like say 100 or 1,000. And let me just do 100 here. So meaning that it's going to be really flat. Okay, the regression coefficient, I believe it's from a normal distribution, but I really don't know where it's going to be. I think it's going to be around 0, but yeah, I don't know like where exactly it's going to be. So you can give it a really large spread, and that will be a way to do weakly informative. And if you remember for regression here, simple linear regression, you also have that sigma that you have to work with, okay, because that's part of the model as well. Today we're going to go into like review a little bit about all of that as well. But really quick here, 1 over sigma squared is the precision, right? And a typical weakly informative prior for that is gamma 1, 1. Okay, so that's what we used to do. So that's one type, weakly informative prior. But you can also get subjective prior. So I might just defer this to you to review what we did before. I mean, because it's very specific to the examples that we did, but there are ways to give subjective prior. And that usually is expressed through, like you have to do some kind of standardization of the data. Like typically, it's not giving prior directly on beta 1 and beta 0, but it's giving, say, particular observations, like with that mean, you think it's going to behave in that way, and then you transfer it back to beta 0 and beta 1. Okay, so I think the short answer is you will try to use prior information if you can, but if you don't have anything, you can use a weakly informative prior. Okay, and I should mention, if you think about the goal, yeah, this is actually a good question, because if you think about the goal of doing Bayesian synthesis, we want to replicate the data as much as we can, right? So in that case, we probably all should just go with the weakly informative prior. Like I have no idea, and I want the data to drive the inference. So then I would just like let the data drive, in a sense that if I give a really weak prior, then I should get estimation or estimates for those parameters that are really just about the data themselves. Okay, yeah. So yeah, I hope that answers your question to some extent. But at the end of the day, yeah, prior choice is important topic in Bayesian inference in general. But I guess for now, we could probably just take it as for synthetic data generation, because we want the data, I mean, we want the estimates to be very close to what the data is telling you. So let's just keep weakly informative prior.
And before we even simulate the synthetic data, because we want to try to find like the best statistical model that can fit, would it be more like a trial and error kind of format where we want to like, it's hard because we're using weakly informative prior, so how can we tell what the best model would be?
Yeah, good question. So actually, let me just pause here so you can all discuss this with your neighbors. And yeah, I said you can just jump in anytime. I'm just going to pause recording here. Yeah, Harry's question is, well, how can we compare models, right? How can we compare synthesizers? And how can we pick the best one? And actually, let me just add like one part to that question. What do we mean by the best one in the first place? Okay, for a synthesis purpose, okay? So take some time. All right, let's hear, well, I sort of wrote down too, maybe there are more questions about this, but I guess what do we mean by the synthesizer in the first place? And then go back to Harry's question, how can we compare different synthesizers? Okay, so I think that might be the right order to answer the question, I mean, to think about the problem. So what do you think? What do we mean by a good synthesizer when we're trying to do this modeling at this stage? What's the goal of doing synthesis? Anyone? Ted?
I don't know. I just thought if we match like summary statistics.
So summary statistics of, I guess, if you have the synthetic data and then the original data, and then you look at summary statistics to see how close they are, okay? So summary statistics. And earlier, I guess, the table that I show you, one of them contains some kind of analysis, like a regression analysis, so we can write those down. Analysis, like coefficients, how close they are. Coefficient. Anything else? Like, we want those to be as close as you can. Is that right?
Yeah.
Anything to add? Isaac, feel free to jump in. Oh, yeah, go ahead.
Yeah. I was gonna say like matching summary statistics such that the disclosure risk from the violin plot is minimized. And like you could have your own like way of putting sort of the priorities of those two in there.
Yeah.
But it would be kind of like a constrained optimization. And I'd also say like making sure the modalities are the same. So it's not like the same. I mean, that's captured by summary statistics, but you want the same shape too. Which like, I guess you could get a similar mean or standard deviation and perhaps not the same shape. There's like two modes or something.
Yeah, so Isaac also brought in, I think, a key here that when we are talking about good synthesizer or not, we not only look at the utility, right? I mean, utility should be good. I mean, especially, well, I wouldn't say should be good. We should want them to be good by doing those Bayesian synthesis, because the Bayesian model is supposed to capture those relationships. I mean, in the data set they're trying to do. And then at the same time, we want to make sure that the risks will be low. Yeah, you want to make sure that the risks are low as well. Okay, so so that's the thing. So it's not only about the utility; it's also about the risks. But I should mention, I think at this stage, especially when we're thinking about what kind of models that we want to put out, we sort of focus on more about the utility. Like you can think about, well, I want to develop a model that works really well, that the utility are super high, and then I go to evaluate my risks. Well, if my risks are too high as well, I might make some adjustment, okay? And typically, like imagine the utility and risks, there are certain, we like to say in this field, that there are certain trade-off between them. I mean, intuitively, well, if the utility is really high, meaning that, well, maybe not only summary statistics, but also regression analysis, whatever that you have, probably means that you didn't add a lot of noise to the data, right? When you don't add a lot of noise, then you probably will still have very high risks as well, right? Because you haven't changed it much. Maybe the risk will be high. But if you notice that, well, I have a synthetic data, I have really high utility, but also really high risks, that trade-off, if that is not acceptable, then you might want to develop like a less good synthesizer, which will produce less utility, but probably will also give you less risk. Okay, so that is the trade-off. I mean, at the end of the day, we'll have to talk about. And from our point of view at this moment, I think let's try to like use the best, if we can, Bayesian synthesis models, if we can develop them, that they can achieve the utility to a really high degree. Because, well, you know that we have to also practice and learn about how to evaluate the risk and utility in the first place, right? So, but from the Bayesian synthesis point of view, we're trying to mimic the data as much as we can. So the goal at this moment is mostly about, well, utility to be high, right? And then come back to the second question, Harry's question, well, how do you compare different synthesizers? Well, in practice, when people are doing it, trying to release some kind of microdata that they possess, I think they just do all kinds of synthesizers and they evaluate what they call the utility profile. Utility profile. And the risk profile of each synthetic data like approach that you have. Okay, and then you have to strike the balance. And sometimes, if you, soonish we're gonna start reading some journal articles, you will see that people try to like do what they call like a utility risk map. That, let's say, utility on the x-axis, risks on the y-axis. You have to like do some kind of like summary of the risk and the utility and then map them. Okay, and usually it's some kind of this shape. I mean, generally, right? I mean, because one increases, the other ones. Oh, sorry, I did it wrong. It should be the other way, right? Right? If you have high utility, you usually have high risks, but you have to find a particular point that is acceptable to you. Yeah, I should mention a lot of times, I mean, if you talk to statistical agencies, they care much more about the risks. In a sense that I have to make sure that my released data does not possess this level of risks. Otherwise, I'm not going to release any of those. But because of that, if the threshold is really low, then you might get some data out there that has really low utility. What you're going to do about it? So I think from a Bayesian modeling point of view, I mean, I don't know what you come to all of this, but from like say people like me, like doing Bayesian modeling in the first place, I think is mostly about the utility at the moment that we're trying to maximize. Okay, but of course you cannot just neglect the risks. You will have to figure out what you're going to do about it. And soon you will see that, well, it really depends on how you assume the intruder knows, how much the intruder knows, and then how you're evaluating the risks. You might have vastly different risk profiles as well. So we just need to, so it's a trial and error process. And I just want to mention that a good synthesizer or any synthesizer has two profiles, the utility and the risk. And at the end of the day, when you compare them, you have to compare them on these two accounts as well as you go forward. Okay? Mm-hmm. All right, that's good. All right, so we're back here. So so the toy example here is a univariate, nothing special, just one variable that we're trying to add noise to from a Bayesian model. So if it's continuous, you can use a normal, and then if we assume sigma is known, so you can only, you just work with mu as the only unknown parameters. But as you can know that, well, if sigma is also unknown, you put a prior for it. And then when you generate synthetic data, you simply have this to be star as well, right? Like you estimate that. Well, JAGs, as we know, going to give you a data frame of all of the draws, right? Like the number of rows, like each row corresponds to iteration, and each column corresponds to a particular parameter. Yeah, we'll see that today with the example, but that's how you're going to do JAGs. Well, if you want to use JAGs, how you can get those posterior draws of the parameters, and from there, go back to the sampling model to do predictions, and that predicted value will be your synthetic data. So get that, I think the flow, working your mind, I think that will be useful. All right, and all right, so this is actually, I mean, this slide actually is tied to what I asked you to do before today, thinking about different ways or different models that you can think of. And so for us, I think we'll encounter continuous variables, binary variables, and categorical variables as we move forward. And I would imagine for your own project, if you want to, when you do synthetic data generation, well, it really depends on which variables you think is sensitive, and then depends on what type the variable is, you will have to go with the most appropriate modeling approach. Okay, so I will defer this slide once I introduce the consumer expenditure data set again, but you will see that in there we have all kinds of types there, and then you will have to determine or like brainstorm what kind of methods you want to do. Sarah?
So this might take us a little bit off.
Go ahead. Mm-hmm.
So if we're thinking about just like the univariate case, but we still want to like have high utility, so in that case, like we're just changing maybe one vector, a variable, or one variable, and leaving the others the same. how do we like account for correlation
Mhm,
between those variables? And
Yeah.
then and then the synthetic variables.
Right. Okay, so let me see. So, okay, let me actually just jump to the next. No, you're fine. I mean, I just wanted to make sure that we have